Hi, everyone. So my name is Hao Xuan, and today I'm presenting my work on adaptive Bayesian changeable analysis with local anomaly detection. So let's get started. So to introduction, changeable analysis refers to detection of changes in distribution of time series. This is becoming an important area to understand the underlying distribution of the data. So in this paper, we try to deal with two challenges that have really made change point algorithm very difficult, which is outliers and heterogeneity. So in this paper, we propose a new algorithm called adaptive Bayesian change point analysis with outliers, short for ABCO, that's really designed to deal with both of those situations. This algorithm can model the underlying time variance signal of the data, distinguish local trends from major changes, detect change points within presence of stochastic volatility and outliers, and flag outliers based on outlier scoring metric. So it's really like a robust method that can work well in a variety of settings and extend the application of change point analysis. Just to give the introduction for the model, suppose we're given a time series y, y1 to yt. The ABCO model decomposes the time series into three different components: a trend component beta t, an outlier component zeta t, and a variance component, noise component epsilon t. And we'll introduce each of these components. So first, starting with the measurement error component. With this component, we follow a stochastic volatility model of order 1. Essentially, here, this is allowed to, for AR1 model on the log scale. This allows you to show to deal really well with regions of high and low volatility. This allows for volatility clustering, which allows it to really adapt locally to changes in variance throughout the time series. The next term is the additive outlier term. And the goal of this term is in order to handle large deviations at specific time steps. So here we use something called a horseshoe plus shrinkage prior. And then the idea here is that we would like the shrinkage, so this term to be close to 0 for most time steps, as outliers should be sparse in nature. However, at very few time steps where there are outliers, we want this term to be very large. So which is the essence of this horseshoe plus, which is a more extreme version of horseshoe shrinkage, in that it pushes most of the way toward either 0, which is a very strong shrinkage, or no shrinkage at all, which allows this term to be very large. So this is the idea in order for us to deal with some outliers that really plague change point algorithms. And finally, for the trend modeling component, here we assume we use a class of global local shrinkage prior under this difference of the state variable beta t. So the beta t sequence is the sequence of interest, which describes the underlying signal in the data. We assume this sequence is either piecewise constant or piecewise linear, dependent on the choice of d. And then we place a shrinkage on the discrete difference of this term. In essence, the idea here is that we want this term, the change here, to be small at most time steps. However, at few certain time steps, we can allow this change to be large. So we use something called like a extension of dynamic shrinkage, which essentially adapts locally. We have two parameters: a global shrinkage that tracks noise at a global scale, and a local variable that adapts to the local noise over time. So this allows us to have additional localized adaptivity in our algorithm. And the key extension here is that we have this term in the equation phi2st, where st is an indicator variable that indicates when the change point occurs. So here, the idea is that we propose it to be based on the log of the difference of the true beta t. Essentially, if beta t exceeds certain threshold, which is estimated through threshold gamma, estimated through the model, then we'll flag it to be a change point. And once we have flagged something to be a change point, we perform a correction on its variance. So the next time step, the variance will be lower. And this is really the key to reduce over a number of false positives in regions of high volatility. In that once we have detected change point, we lower the variance so that we accept differences. So we have gaps between change point. To illustrate an example, this is like the performance of the algorithm in the data. Here we have 4 change points. We can see that we can, despite regions of high and low volatility, we can produce a very smooth underlying trend. As we can see here by the red line, which is the omega t, in that it spikes up at the presence of a change point, then it comes back down as a result of the threshold variable. So yeah, thank you for and that's the presentation. Thank you.